All right, so let's go ahead and continue from our discussion. We are in the middle of deriving our kinematic equations with calculus. So we started with this equation here, that acceleration is the derivative of velocity with respect to time. And we integrated both sides to get our velocity equals acceleration times t plus a constant. Now to solve for that constant, we can go ahead and state that at v of 0 seconds is the same thing as saying v naught, okay? And so we'll set that equal to this side here. So a times 0 seconds plus our constant, we'll call that c1. This just means that our v naught is equal to our c1 or our constant. Therefore, v of t equals a times t plus our constant or v naught, our initial velocity. Okay, so we'll do the same thing again. We'll say that v is equal to the derivative of x with respect to t, okay? And we will take the integral of both sides, so we will need to move this over, the t dt, so that we get dx equals v dt, and then integrate, okay? And we'll need to plug in our v here, so that's a t plus v naught multiplied by dt, and we get x equals 1/2 a t squared plus v naught t plus another constant, c2 we'll call it, okay? We'll do something similar here and say that x of 0 is equal to x naught. So we'll plug in t equals 0, and you can see that it'll be 0 plus c2. Therefore, we can solve for x of t is equal to 1/2 a t squared plus v naught t plus x naught. So this one here and this one here are our kinematic equations derived through calculus. All right, so now we're going to look at our final example here, example 3.17. It states a motorboat is traveling at a constant velocity of 5 meters per second when it starts to decelerate to arrive at the dock. Its acceleration is described here. So it equals negative, this should be 1/4. So I'm going to write that again. Our acceleration with respect to time is negative 1/4 t. Okay? So the first part asks, what is the velocity function of the motorboat? So what we'll do is we'll do something similar to what we were just doing. Velocity is going to be the integral of a dt, okay? Or dv equals the integral of a dt. So we have v is going to be the integral of negative 1/4 t with respect to time. So we get negative 1/4 times 1/2 times t squared plus a constant. Okay? Now remember that our velocity, our constant, or our velocity in the beginning of the problem, v naught, is the same as v of 0, is 5 meters per second. Okay? So if we plug this in, or equate this with our equation here, we get negative 1/8 times 0 squared plus c1. Therefore, our constant here, c1, is equal to 5. Okay, so our velocity with respect to time is equal to negative 1/8 t squared plus 5. Okay, whoops. Okay, so that is for part A. Now part B states at what time does the velocity reach 0? So we want to find out where the velocity is equal to 0. Okay, so what we do is we just equate that to our velocity equation here, negative 1/8 t squared plus 5, and solve for time. So t is going to then be, or t squared I can put, doing some algebra, subtracting that over, multiplying by 8, and then negative, we get t squared equals to 40. Take the square root, and we get t equals 6.3 seconds. Okay? Alright, so now we've done part B. Let's move on to C. It states, what is the position function of the motorboat? So we will go ahead and take our velocity function and integrate it to find our position function. Okay, so let me go ahead and do that over here. So x of t will be the integral of v dt. Okay, so the integral of negative 1/8 t squared plus 5 dt, which is going to be negative 1/8 times 1/3 t to the third plus 5t plus c2. Okay, and again we will say that x of 0 is 0, since we can just claim the starting position of the boat is at 0 meters. Okay, so then if we plug this into that equation, 0 equals t, or t equals 0, we get 0 plus 0 plus c2. Okay, therefore c2 is equal to 0. Okay, so our position function is negative 1/8 times 1/3 is negative 1/24 t cubed plus 5t. So that is our position function. Now moving on to part D, it states, what is the displacement of the motorboat from the time it begins to decelerate to when the velocity is 0? So what is the total displacement? Okay, so what we will do is we will plug in the amount of time it takes for the boat to stop. Okay, so we'll say x of 6.3 seconds and plug it in. So negative 1/24 times 6.3 cubed plus 5 times 6.3. And then our position will be, after we plug that into our calculator, is 21.1 meters. So this is our final displacement. Okay. Okay, so the last part I'm not going to physically do, but I will show you what the book has. So it says graph the velocity and the position function. So that's what these are. So this is my velocity function and my position function. Okay, so I'm going to go ahead and show you what that looks like. So this is the velocity function with respect to time. Okay, and this is the position function with respect to time. So this is just to show you guys, I guess, how this works. You can either use like a Google, I think in Google you could search like graphing calculator. That'll work fine to do this. You can probably do it in Excel, but whichever way you'd prefer, it's just to show you that you can do that. Okay? All right, and that is the end of the PowerPoint. So I will post this, and if you have any questions, feel free to contact me.